Welcome back. In this example, we're gonna find the relative extrema for this function. In a quick reminder, sort of kind of like what we have developed over the last few problems in this section, is a strategy known as the first derivative test for extrema. And this process, we have to follow sort of like a strategy. And to summarize it, I label it and summarize it in this box. First, we're gonna find the critical numbers of the function, and that is by finding the derivative of the function, and then to examine the values of the derivative on the left side of the critical numbers and the right side of the critical numbers, and we're gonna see what happens to the signs of the derivative on the left side and on its right side. So we want to see whether there's a change in the sign of the derivative, whether it's positive to negative, whenever you have a critical number. So whenever that happens, when it goes from positive to a negative value, then that's considered to be a local max for that function at that point. And if the derivative changes from negative to a positive, then at that critical number, then you're gonna have a local min at that point. And if there's no change in the derivative, meaning if that goes from negative to negative and positive to positive, then at that critical number you won't have neither, right? You're not gonna have a local max nor a local min. So let's jump into this example 3. And let's find the relative extrema for this problem. First, we're going to find the intervals where the function is increasing, decreasing, which is most of the work of finding the relative extrema. So we'll begin by finding the critical numbers. Find critical numbers. And remember that we find the critical numbers by doing two things, right? I'll put a double here. So we find that whenever the derivative, in this case we're using k, whenever the derivative is equal to 0, or the values of x when the derivative is undefined. Right, so we're finding when does this happen. Now here we have a polynomial, and we're going to end up getting a polynomial as a derivative. So we're going to find out that the second case won't work. But let's go ahead and find the critical number, the derivative first. Find the first derivative by using power rule. Bring down the power of 4 times x raised to the third power, plus 16 times 3 is 48 times x, and then raise it to the power of 2, right? We subtract 1 from the power. And often when you're looking for critical numbers, it's almost a routine step to factor this out. And we notice that we have a factor of 4 and x squared. So we're going to factor those out. So what's left behind? We're left with an x in the first term plus 12 in the second term, right? And you can always double check by multiplying back and getting this result. All right, so this is the derivative, and if you notice, the derivative is a polynomial, as we mentioned before. This is a polynomial because the power of the variable are all positive whole numbers. So therefore, there won't be this case, right? There won't be no critical numbers for this case because this is always defined. So let's begin by finding the critical numbers when k prime equals 0. So we're going to set k prime equal to 0. So that implies that we have 4, and I can use this one or this one. So we're going to use the one that is factor, and we're going to set this equal to 0. So set this equal to 0. And the reason why we're doing this is so we can find the critical numbers. So then let's, by the zero factor property, this suggests we could we could find the zeros of this by setting this equal to 0. And so pretty much we take every factor and we set it equal to 0. Now we already know that this is not going to be a case because 4 cannot equal 0. And for this one here, then we know that if you take the square root on both sides, then you will get x equals 0. Or another way you can think about it is, the only way that you can multiply a number by itself, right? Because remember what x squared means, x times x. The only way you can multiply a number by itself and get 0 is whenever this is 0, right? Whenever this is 0. So x has to equal 0. And then lastly, this would happen whenever we subtract 12 on both sides of the equation. And we end up getting x equals negative 12. All right, so the critical numbers, I'm just going to say Cn. The critical numbers are 0 and negative 12. And we should verify that these are critical numbers. Just because they're equal to 0 doesn't mean they're automatically critical numbers. We have to make sure that these numbers are part of the domain of the function. And it is, because this is a polynomial, and a domain of all the domain of any polynomial function is all real numbers. So that means it would include this number and this number. All right, so let's go ahead and find when is the function increasing, decreasing. The way we're going to do this is by creating a number line, and then subdivide this number line using the numbers we just found. So remember that negative 12 is to the left side of 0. So these are my x values. This is my derivative values. So whenever x equals negative 12, the value of the derivative is going to be 0. Why? Why do we know that? Because that's actually how we found them, right? We found the values of x that makes the denominator be 0, right? The same argument will follow with x equals 0. The derivative will be 0. So the question is, what happens in between those intervals, or in those intervals? We can see here that we have 1, 2, 3 intervals, right? This, and this, right? So we have those 3 intervals, so we have to test those 3 intervals. And we're going to choose, of course, numbers that are easy to test. But again, you can choose any number you want to, as long as in those regions, right? So I chose negative 13, negative 1, and 1 to find the critical numbers. So we're gonna test. So what are we looking for? A lot of times students will get kind of lost in what are they looking for. Remember what we're looking for. We're trying to figure out whether the function is increasing, decreasing. And we can do that by determining whether the derivative is positive or negative. So we want to know whether this is positive or negative, positive or negative, positive or negative. That's all we care. So let's go ahead and maybe rewrite the derivative function. I'm going to write it in terms of in its factor form, because that's actually the most convenient and more practical way to use it. And then we're going to test some numbers, right? So we're going to say what happens for the derivative at negative 13, what happens to the derivative at negative 1, and what happens to the derivative at 0. We're looking for the sign value. So what we could do, and maybe sometimes students will take this for granted, is to make some logic. Let's use some logic. So what I mean by this, we're only trying to determine whether this is positive or negative, right? That's the question for these different cases. Well, we already know something about this function. We already know that that 4 is a positive number. So that factor 4 is already a positive number. And we also know that x squared is also going to be a positive number. Why? Because if you have a negative number being square, then it turns into a positive number. So we already know that the product of those two is going to be the product of two positive numbers. So we have, in a way, sort of something of this form, right? So if we write this node, this will make everything much easier because we don't have to think too hard anymore. So we're going to replace the x's with negative 13. So we have plus times negative 13 plus 12 is going to be a negative number. And so positive times negative is negative. Remember that you pretty much all you gotta do is, if you're multiplying an odd number of negatives, then this is going to be a negative. If you have an even number of negatives, right? Let's say you have plus times negative, even, that means they're common pairs. So then that means that this is going to turn into a positive. So so I'll try to remember do that on the next problems. Then we have negative 1 plus 12, and then we have positive times, and negative 1 plus 12 is positive 12, so we end up getting positive 12. The next one, we have positive 12 times 0 plus 12. And, well, we're going to get a positive number from here. So we get positive times a positive times a positive equals positive. So if we go back to the board here, and we are writing our notes, then we're going to say that for the first region, whenever we're testing any number in here, the value of the derivative is going to be negative, right? As we see here. Then anything between negative 12 and 0 will be a positive. And anything between 0 and I think I made a silly mistake here. I meant to have positive 1. So alright, so like that, right? So, but the still it's going to be a positive, right? Positive times positive, and then 1 plus 12 is positive, so we get a positive. So, sorry about that. And then you can kind of make an additional note here and see how this is going to look like for the function. What we said is that if the derivative is negative, that means the slope is negative. That means the function is decreasing. If the derivative is 0, that means the slope is 0, which means the function is horizontal. If the derivative is positive, that means that the slope is positive, so therefore the function is increasing. If the derivative is 0, that means the slope is 0, which means the function is horizontal. And then finally, if the derivative is positive, that means the slope is positive, which means that the function is increasing. Right. So if you can kind of see this, it kind of almost looks like this, right? Right. So we see that sort of kind of maybe a little bit of the behavior of the function. But anyways, what we were asked is to find where is the function increasing and decreasing. So if we look at back here, it's increasing only when it's going up, right? So it's between negative 12 and 0, and then from 0 to 1. So we can say from negative 12 to 0, and from 0 to 1. And then lastly is decreasing from negative infinity to negative 12. Now we could argue that we can actually add this one to be from negative 12 to, and I mean 1. Actually, I meant infinity. Sorry, I meant infinity from here because it's going from 0 to infinity. We could argue that we can actually do this one from negative 12 to infinity. It just depends on which textbook we're using. So it's one or the other one, right? All right, and so, but this is also giving us information regarding to the relative extrema. We can see here that we're gonna have a relative min, right? Relative min at x equals negative 12. So at x equals negative 12, we're gonna have a relative min. That means this is not the relative min. We're just saying that there is a relative min at x equals negative 12. And the other option would be, what about x equals 0? Well, this is not a relative min nor a relative max, because we can see that there's something smaller than that, also something bigger than that. So this one is going to be none. All right, and so that is the conclusion. So the conclusion for this one is that we have no relative max, and we have one relative min. All right, and so I hope you guys found this helpful, and please let me know if you have any